Hi everybody, we continue our discussion on the basic definitions of the thermodynamics. Today we look at the thermodynamic variables. We start with thermodynamic variables. What are the thermodynamic variables? Quantities like pressure, volume, temperature, internal energy, entropy, number of moles, which determine the state of a system, These are called the thermodynamic variables or the quantities. Pressure, volume, temperature, energy, entropy, number of moles. So these are the variables that we use to describe the state of a system in thermodynamics. And they can be classified into two broad categories. The thermodynamic variables can be classified into two broad categories. One is extensive variables, the other is intensive variables. Extensive variables and intensive variables. So what are extensive variables? Variables which depend on the system size, like mass or volume. These variables are called extensive variables. The example, energy, entropy, number of moles. These all depend on the size of the system. So if you divide the system into two equal parts, the value of each of these variables, that will be half of the value for the whole system. Suppose you have a system like this. Suppose its total internal energy is U, and you divide the system into half. This one will have U by 2 energy, and this will have U by 2 energy. Same way, entropy, the total entropy S, this will have S by 2, this will have S by 2. So this property or this variable depends on the size of the system. So such variables are called the extensive variables, or energy, entropy, number of moles. These are all extensive variables. Now come intensive variables. What are intensive variables? Intensive variables are variables which do not depend on the system size. Temperature. This is an example for an intensive variable. Rho or density, this is example for an intensive variable. Suppose you have a system like this. Suppose its temperature is T, and you divide the system into two halves. The temperature of each part of the system will be T. There will be no change in that. The temperature does not become T by 2 or T by 2, T by 2 and T by 2. The temperature remains a constant T. And this is true for density also. If you divide the system into half, if you reduce the size of the system, its density will not change. So such variables are called intensive variables. So the thermodynamic variables which determine the state of a system can be divided into intensive variable and extensive variable. Then the equation of state. What is meant by the equation of state? Any relation between any three thermodynamic variables of the system, relation connecting any three thermodynamic variables of a system, this is called the equation of state. For example, for a perfect gas, we all know we have the equation PV equal to RT. Same way for a real gas, we have P plus A by V square into V minus B equal to RT. So these are all equations of the state, relation connecting any three thermodynamic variables for the system. Okay, so that is equation of state. Then we discuss about the thermodynamic equilibrium. What is meant by thermodynamic equilibrium? In many topics which are we going to discuss later, we might be using the term thermodynamic equilibrium. Thermodynamic equilibrium. So we should know the exact meaning of what is meant by the thermodynamic equilibrium. A system in mechanical equilibrium, thermal equilibrium, and chemical equilibrium. A system which is in mechanical equilibrium, thermal equilibrium, and chemical equilibrium is said to be in thermodynamic equilibrium. Said to be in thermodynamic equilibrium. So what is meant by the mechanical equilibrium? Suppose we have a system, and the surroundings. If there are no unbalanced forces, existing between the system and surroundings, okay, system and surroundings, and between the different parts of the system, then we say the system is in mechanical equilibrium. So if no unbalanced forces exist between the different parts of a system and between the system and surroundings, we say the system is in mechanical equilibrium. Then what is thermal equilibrium? The temperature of all parts of the system is same and it is identical with the surroundings. It is identical with the surroundings. Then we say the system is in thermal equilibrium. Then chemical equilibrium. If there is no change in density or in its chemical composition, the chemical composition of the system is same. Everywhere the chemical composition is same and there is no change in density, we say the system is in chemical equilibrium. So if a system is in mechanical equilibrium, non-balanced forces exist, thermal equilibrium, then chemical equilibrium, then we say the system is in thermodynamic equilibrium. Okay, so that's about equilibrium. Then we have the thermodynamic process. What is thermodynamic process? We know the state of a system is specified by the thermodynamic coordinates. So at any instant, the state of the system in thermodynamics is specified by the thermodynamic coordinates. Now, any change in the thermodynamic coordinate causes a change in the state of the system. So, any change in the thermodynamic coordinate causes a change in the state of the system, and that change in the thermodynamic coordinate or that change in the state of the system, that is called a thermodynamic process. Okay, so this is called thermodynamic process. So any change in the thermodynamic coordinate, pressure, volume, temperature, that causes a change in the state of the system. The state of the system is determined by the thermodynamic coordinates. So that change in thermodynamic coordinates, which causes a change in the state of the system, that is called a thermodynamic process. Okay, a thermodynamic process is shown in an indicator diagram here. Okay, we have the pressure here, we have the volume here. So if you take any two variables, and if you denote the change in variables or the change in state of the system, using this we have the indicator diagram. Okay, so here we see the pressure and volume changing. It is changing from A to B. Okay, so there is a change in state of the system. The thermodynamic variables, pressure, volume are all changing. Okay, now this is also a way of thermodynamic process. Here see, you have A, B, C, D, E, So A to C, the thermodynamic variables are changing. So that's a process. C to B, that's a thermodynamic process. Here also thermodynamic process. See A to B through E, that's a thermodynamic process. So you can describe the state of the system using this PV diagram. Okay, PV diagram is generally called indicator diagram. You can have a temperature entropy diagram. Okay, so an indicator diagram is actually a graph between any two variables. Okay, it can be pressure and volume. Okay, or it can be temperature and entropy, or it can be pressure against temperature. So if you draw the change in state of a system using any two of the thermodynamic variables, you have the indicator diagram. Okay, any point in the diagram specifies the state of the system. Then another term that we frequently use is the quasi-static process. Quasi-static process. So what is a quasi-static process? We know what is a static process, something which does not change. Okay, that is static. Then what is quasi-static? A process in which the system successively changes from one equilibrium. We know what is meant by equilibrium. Okay, thermodynamic equilibrium. A process in which the system successively changes from one equilibrium state to the next equilibrium state, differing only infinitesimally. That is, the state, the thermodynamic variables specifying it, that changes by a very small amount, infinitesimally small amount. Okay, and if it is that change taking place at an infinitesimally small rate, that means it takes long time for a very small change in the thermodynamic variable. Then we say the process is a quasi-static process. So the system successively changes from one equilibrium state to the next equilibrium state, differing infinitesimally. Small change in pressure, small change in volume, very small change in temperature. And this small change in pressure, volume, temperature takes place at a very small rate, that it takes a lot of time for the change to take place. Such a process is called a quasi-static process. Then comes the isothermal process. What is an isothermal process? You all know that. A process in which pressure and volume change at constant temperature is known as an isothermal process. So, constant temperature. Okay, a process in which other variables changes except the temperature. The temperature is constant. That is known as an isothermal process. So we have a system and we have the surroundings. Okay, and suppose that the system is separated from the surroundings by a diathermal wall. Okay, by a diathermal wall. That means through the diathermal wall, heat can easily flow. Okay, diathermal wall permits flow of heat through it. Okay. So the system can exchange energy with the surroundings. Now, a heat transaction. There will be heat transaction between the system and the surrounding. The system is in very good thermal contact with the surrounding. Then the process is an isothermal process. Why it is an isothermal process? Suppose some changes take place in the system. The state of the system changes, pressure, volume, temperature changes. Then what happens is immediately the excess heat will flow from the system to the surroundings, maintaining temperature a constant. Okay. Now if in a process the system cools down, its temperature, heat decreases, here temperature decreases, immediately heat will flow from the surroundings into the system, maintaining a constant temperature. So for this heat transaction to take place between the system and the surroundings, the system must be enclosed by a diathermal wall. Okay. Example, we have perfect gas taken in a cylinder. The cylinder has a diathermic wall. This is diathermic wall. This is a cylinder. We have taken perfect gas in the cylinder. This is the piston. When you push the piston inwards, this gas will be compressed. Okay, so we will be doing work on the system, and it gets energy and its temperature increases. But what happens is the excess heat will flow from the gas into the surroundings through the diathermic wall. Okay, keeping the temperature a constant. And during expansion process, the reverse thing will happen. During expansion process, work is done by the gas. The gas will be doing work, and it cools down, and the excess, heat will flow from the surroundings into the gas, maintaining a constant temperature. Okay, so this is an example for an isothermal process, and one point that we have to note down is, for an isothermal process to take place, the system must be enclosed by a diathermal wall. The equation of state for an isothermal process for perfect gas, that is PV equal to constant. We know for a perfect gas PV is equal to RT. This is the equation of state. Here this temperature is a constant. Since temperature is constant, we have PV equal to constant. So if you draw a graph between the pressure and volume, in this case, you will have a shape like this. If you increase the pressure, the volume decreases because PV is a constant. Okay, so if you increase pressure, volume increases. If you decrease pressure or the volume, if you decrease the pressure, volume increases. PV is a constant. This is called an isothermal. Okay, this is called an isothermal. Okay, and it represents an isothermal process. Isothermal, it's like this. Then, in the case of the perfect gas, we are taking perfect gas. Its energy depends only on temperature. Temperature is actually, we have seen, temperature is actually a measure of the average kinetic energy of molecules. Okay, average kinetic energy of molecules. In the case of perfect gas, the potential energy is 0. So internal energy is entirely kinetic energy. Internal energy is actually kinetic energy plus potential energy. But here it is simply kinetic energy because there is no potential energy, there is no interaction between the molecules in a perfect gas. So we say as the temperature remains constant here, there is no change in the internal energy for a perfect gas. Okay, so that's about isothermal process. Then comes the adiabatic process. So what is an adiabatic process? A process which occurs without transferring a heat or mass between the system and surroundings. Okay, a type of thermodynamic process which occurs without transferring heat or mass between the system and surroundings. Okay, so what happens here is the system is completely isolated from the surroundings. It's isolated from the surroundings so that heat neither enters or leaves the system. Heat neither enters or leaves the system. Here the pressure, volume and temperature, the temperature may change. In the isothermal process, the temperature is fixed, but here the temperature will change may change. Pressure, volume, temperature, all the quantities can change. Okay, we will later on see in adiabatic process the quantity remains, only a single quantity remains constant. Okay, so anyway, here pressure, volume, temperature change, the system is isolated from the surroundings. Okay, for example, a perfect gas enclosed in a cylinder. Okay, perfect gas enclosed in a cylinder fitted with a piston. So you see, we have an insulating wall, perfectly insulator. Okay, the wall is perfect insulator, so there is no exchange of heat between the system and the surroundings. So there is no exchange of heat. Okay, exchange of heat does not take place. So if you compress the gas, we are doing work on the gas, so it gets energy and its temperature will rise, and that temperature will not change because there is no exchange of heat between the system and surroundings. Here, heat cannot flow from the system into the surroundings, so the temperature will change. Similarly, if you move the piston outwards, there will be expansion and there will be temperature decrease. Okay, so that heat will not flow from the surroundings into the system, so that temperature change remains. So here pressure, volume, temperature, everything changes. This is because the work done is converted as the internal energy. Okay, when the gas is doing work, its internal energy decreases. When we do work on the gas, its internal energy increases. So there will be change in temperature. So this is an example for the adiabatic process. Then in practical cases, any sudden or quick process is an adiabatic process, because the system will not get enough time to communicate or to transfer heat with the surroundings. So if there is a quick process, if there is a very sudden process, then it will be an adiabatic process. For example, bursting of an inflated motor car tire. Bursting of an inflated motor car tire, that's an example for an adiabatic process. That's a very quick process, and the system, the gas in the tire, that will not get enough time to transfer the heat energy to the surrounding to maintain the temperature constant. So that's an example. Then compression and expansion of a working substance in a petrol engine or diesel engine. In a diesel engine or petrol engine, the compression and the expansion of the working substance take place, and that's an example for the the adiabatic process. Okay, in an engine, petrol engine or diesel engine, the piston is continuously moving at a very fast rate, and that's an example for an adiabatic process. And the equation of state for an adiabatic process of a perfect gas is, in the case of perfect gas, the isothermal process, we know the equation for isothermal process is PV equal to constant. Here we will be getting PV to the power gamma, PV to the power gamma, a constant, where gamma is the ratio of the specific heats. So this is the equation of state for adiabatic process of a perfect gas, PV raised to gamma, a constant. So we will be later on deriving this relation. Okay. So that's about the adiabatic process. Now comes isobaric process. We all know that isobaric process is a process taking place at a constant pressure. This is known as isobaric process. So if you take an indicator diagram here, we see the AB. AB, this represents the isobaric process. Okay. Then isochoric process, a process taking place, we all know that at constant volume, that is called an isochoric process. Okay, that's an isochoric process. Here the BC represents the isochoric process. Okay, that's an isochoric process. See here the BC is parallel to the pressure axis and the volume is fixed. So that's an isochoric process. Then a cyclic process. It's an important process, a process in which a system is taken from an initial state, okay, initial state, through a succession of states, but is always brought back to the initial state. So starting from an initial state, it goes through several states and finally it comes back to the same state. That's a cyclic process. Carnot cycle, you would have studied Carnot cycle is a cyclic process. It comes back, the system comes back to the initial state. Okay, so here in the indicator diagram, it can be represented like this. You start from the point A, you go like this and come back to A. Okay, so you have the cyclic process. So it's represented by a closed path. See, it's represented by a closed path in the PV diagram. Closed means, the graph that comes back to the initial state. So there is no change in the state of the system at the end of the cycle. So at the end of the cycle, there is no change in state of the system because you are coming back to the same state. That means the change in internal energy, that is equal to zero here. Okay, so in a complete cyclic process, the change in internal energy equal to 0 because the internal energy, that is a function of the state variables. Okay, that's a function of state variables, pressure, volume, temperature, like this. So since you are coming back to the same state, there is no change in these variables. Okay, so we say the internal energy change, that is equal to 0 because internal energy depends only on the state of the system. Okay.